Hi everybody, I'm Rashid and I continue this series of these videos in finite math, and now I continue the talk about calculating probabilities of events, right? Calculating probabilities of events. And in this topic, probability with equally likely outcomes, just like the previous example of the rolling a die. They have equal chance of being a face with 1 or a face with number 6, for example. So in this case, let S be a sample space consisting of n equally likely outcomes. Let E be any event. Then if n of E is the number of outcomes in E, so NE or is the number of outcomes in E, then the probability of the probability of E is NE over N, which is the number of outcomes in E divided by the number of outcomes in the space, the sample space. And let's do an example on it. So an urn contains eight white balls here and 2 green balls. A sample of 3 balls is selected at random. So you have 8W, you have 2 green, and a sample of 3. Let's do B for them, right? 3 of B are picked or selected, right? So the total, this will show you the total, that is 10, and you're taking 3 out of 10. So what is the probability that the sample contains only white balls, right? So you want to think about it? Is it going to be 3 out of 8, right? So think about it for a second. And now we do this at least. This is another topic. So if you look at the previous videos, the outcomes of the events, and here we're not talking in specific order, right? We're just saying taking 3W out of the 10. So it looks like a combination, right? So a probability of the event E that we're interested in is a number of the outcomes in E over N, which is the number or total outcomes in the sample space. So here it's a combination of taking 3 out of 8. Since we're interested in W, right? The top one, you're taking from 8. So what are these combinations of taking 3 out of 8? That's what we need to know. What is number of outcomes, right? Over the sample, over the number of outcomes in S. So once you figure out the top, then this one, of course, is just going to use the same thing. You're taking 3, but from 10, the total in the sample space. And if you use the formula from the previous videos, I would recommend to check them and use the factorials. For this combination formula, you should get a 56 divided by 120, which is 7 out of 15. And 7 out of 15 decimal, it's 0.004 for 6, 6. Let's say we want 2 places, for example, 0.47, which means 47%, or you do 46.67%. That's probably better, right? Because if you keep doing this, then when you multiply it, this is much better than using this 47. But of course here we're going to leave it this way, right? So we're learning also how we present the answer and how accurate it's going to be. This is an exact answer for giving the probability number, but if you're asked for the percent number, then it's going to be in this case an approximate number, and you need just to watch for the instructions, right? So another example. So another example. Let's call this one here in 1 and 2. This is about medical screening. Suppose that a cruise ship returns to the United States from the Far East, unknown to anyone. 4 of its 600 passengers have contracted a rare disease. And we've seen now these stories happening, even with the coronavirus. Let's just say 4 out of 600 passengers have contracted a rare disease. Suppose that, of course, coronavirus is not a rare disease now, it's pandemic. Whatever illness. So for the problem here is a story, then you start, like for here, maybe this, all this is extra here. But 4 out of 600 is not extra, that's going to be used. Whatever rare disease or not, is not important. But the illness is 4 or L out of 600. Suppose that the Public Health Service screens 20 passengers selected at random to see whether the disease is present aboard ship. What is the probability that the presence of disease will escape detection? So you see, this is a very interesting topic, because if you want to buy time and you want to act, you want to do something like this, but you want to know this approximation you're going to do, how how accurate it's going to be, especially if screening all the 600 will take longer time, and the return of the results may, take even longer. But you need to make a decision right away. So let's say here a decision was made that's by this Public Health Service to screen 20 passengers at random to see whether the disease is present aboard the ship. So what is the probability that the presence of disease will escape detection, right? So what do you think? Based on example 1, it just looks like you're taking at random, right? So the sample space here consists out of 20 drawn from 600, right? There are, for the combinations, that's how many samples you're going to have. So let's write it down. You're going to take 20 out of 600. So that's how many samples you're going to have. The counting method that we used in previous videos. So the number of samples containing none of the sick passengers is so once you test 596, 20, so the number of samples contain none of the 6 passengers is a combination of this 20 out of this 596. Therefore, the probability of not detecting the disease is, let's write these. So now the probability so now we're gonna compare this by all the samples that are taken, and it better be high, right? Because 20 taking 20. I'll explain a little more this, but I just want to break it down. Then we would need to go back to it and explain it again, because some of these may look fuzzy, but definitely we need to see the previous videos about counting and combinations and computations in order to understand how we did the calculations here. All right, so and this kind of stopped. All right, so let's explain it again. So what is the probability that the presence of the disease will escape detection? Right. So suppose that the cruise ship returns unknown to anyone, 4 out of 600 passengers. So you see this unknown to anyone. 4 of its 600 passengers have contracted a rare disease. So suppose that the service wants to screen 20 passengers to see whether the disease is present. What is the probability that the presence of the disease will escape detection? So so the counting of the samples of this combination is 20 out of 600, and once you start the screen, that means you have 20 out of 596 containing none of the sick, because that's what the question is about. Then the probability of not detecting a disease will be, of course, the ratio, and once you put it together, you get 87%, which is so it's kind of, you make a decision: is that bad or is that good? It's kind of bad because 87%, you know, is the likelihood that the presence of the disease will escape detection. All right. So so what else to explain here? The question as well, of course, now that you look at it a few times, you're going to say, what about this 596, where it came from? Well, you see the number 4, unknown to anyone, but we assume that 4 out of 600 are sick, right? If 4 out of 600 are sick, that means the ones that are not sick, right, are 596. So if you take 20 out of this 596, that's the combination there, right? So, so that's the counting for these events, right? And that's the question. It's what is the probability that the presence of disease will escape detection? Escape detection means whatever you pick, one the sick, people. So that's 600 minus 4 equal 596, and we use that there. And of course, like the formula says, this is the sample space. All right, and I think this is done. We'll go ahead and stop this. Thank you.